Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on graph theory, lecture number 40, in which I will solve some more problems on Euler's formula and planar graphs. Now we solve a problem. Problem is for a connected planar graph with n greater than equal to 3 vertices, so that 5 capital V1 plus 4 capital V2 plus 3 capital V3 plus 2 capital V4 plus capital V5 is greater than equal to capital V7 plus 2 multiply capital V8 plus plus k minus 6 multiply capital Vk plus 12, where capital VR denotes the number of vertices with degree r and k is the largest degree of a vertex in G. Since given that the graph G is connected and planar, in which number of vertices equal to capital V, number of edges equal to capital E, and number of regions equal to capital R. Since given that number of vertices V, capital V equal to n, this is greater than equal to 3. Since graph is connected and planar and n greater than equal to 3, therefore degree of each region is greater than equal to 3. Since total sum of degree of all regions equal to 2 multiplied by E, therefore 3 multiplied by number of regions less than equal to 2E implies that R less than equal to 2 by 3 E. This is number 1. Also, by Euler's formula, V minus E plus R equal to 2 implies that V, capital V, minus E, in place of R, if we write 2 by 3 E, then left side will be greater than equal to 2, implies that V minus E by 3 greater than equal to 2, implies that 3V minus E greater than equal to 6. This is number 2. given that VR, capital VR, equal to number of vertices with degree R. Therefore, sum of vertices of degree 1, degree 2, degree 3, if the K be the largest degree of the vertex, then plus dot 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 Vk equal to capital V. Therefore, capital V1 plus capital V2 plus dot 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 plus capital Vk equal to capital V, total number of vertices, where K be the largest degree of a vertex in graph G. Let this is number 3. Therefore, total sum of degrees of vertices equal to V1 be the number of vertices with degree 1. So here we write 1 multiplied by V1. V2 be the number of vertices such that each vertex is of degree 2. So 2 multiplied by capital V2 plus dot 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 plus K multiplied by capital Vk. Let this is number 4. Since total sum of degrees of all vertices equal to 2 multiplied by number of edges equal to 2e. This is number 5. From 4 and 5 we get capital V1 plus 2 capital V2 plus dot 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 plus K capital Vk equal to 2e. This is number 6. Putting values of 3 and 6 in 2, we get 3 multiplied by capital V. Here in number 3, capital V1 plus capital V2 plus dot 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 capital Vk minus E. E is 1 by 2 V1 capital V1 plus 2 capital V2 plus dot 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 plus K capital Vk. This is greater than equal to 6. Implies that here taking LCM, 6 capital V1 plus capital V2 plus dot 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 plus capital Vk minus V1 capital V1 plus 2 capital V2 plus dot 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 plus k capital Vk. This is greater than equal to 12. Implies that 6V1 minus V1 plus 6V2 minus 2V2 plus 6V3 minus 3V3 here plus 6V4 minus 4V4 plus 6, here we have V5 minus 5V5 plus 6V6 minus right side 6V6 plus 6V7 minus 7V7 plus 6V8 minus 8V8 plus dot 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 plus 6VK minus KVK. This is greater than equal to 12. Implies that here 6V1 minus V1 equal to 5V1, 6V2 minus 2V2 4V2, 6V3 minus 3V3 3V3, 6V4 minus 4V4 2V4, 6V5 minus 5V5 V5, 6V6 minus 6V6, this is 0. Here we see that 6V7 minus 7V7 is minus V7. We take this negative quantity right side. This is greater than equal to V7. This is 6V8 minus 8V8. This is minus 2V8. We take this negative quantity right side plus 2V8 plus dot 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 plus here we take common Vk 6 minus k, we take right side, then k minus 6, k minus 6 Vk plus 12 implies that 5V1 plus 4V2 plus 3V3 plus 2 V4 plus V5 is greater than equal to V7 plus 2V8 plus dot 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 plus K minus 6 Vk plus 12. Proved. Now we solve the next problem. Next problem is so that a simple planar graph with less than 30 edges has a vertex of degree 4 or less. Now we solve this. Solution. Since given graph is simple and planar, if possible, let degree of each vertex is 5 or greater than 5. Therefore, total sum of degree of all vertices greater than equal to 5 multiplied by number of vertices V, where V equal to number of vertices in the given graph. Let this is number 1. Since total sum of degrees of all vertices of a graph equal to 2 multiplied by number of edges equal to 2 multiplied by E, where E equal to number of edges of given graph. This is number 2. From 1 and 2, we get total sum of degree of all vertices of the graph is 2e. Here 2e greater than equal to 5v. This is number 3. Let R equal to number of regions of the given graph. Since the graph is simple and planar, therefore each region is bounded by 3 or more than 3 edges. Therefore, degree of each region is greater than equal to 3. Let this is number 4. Therefore, total sum of degrees of all regions is greater than equal to 3 multiplied by number of regions are, since total sum of degrees of all regions is 2e greater than 3r, implies that r less than equal to 2 by 3 e. This is number 5. From 3 we get v less than equal to 2 by 5 e. This is number 6. Since Euler formula for a planar graph is v minus e plus r equal to 2. This is number 7. Using 5 and 6. In 7 we get here v less than equal to 2 by 5 e. In place of v we write here 2 by 5 e minus e. In place of r we write 2 by 3 e. Then left side will be greater than equal to 2. Implies that here 15, here 6e minus 15e plus 10e greater than equal to 2 implies that here 16e minus 15e greater than equal to 30. This is number 8. Since given that our graph has less than 30 edges, but in 8 we get number of edges greater than equal to 30. Therefore we get a contradiction. Therefore our assumption that each vertex is of degree 5 or greater than 5 is wrong. Hence, there exists at least one vertex whose degree is 4 or less than 4. Proved. Now we solve the next problem. Problem is, let G be a graph with 11 or more vertices so that either G or its complement G bar is non-planar. If possible, let the graph G and its complement G bar both are planar. For G to be planar, we have E less than equal to 3V minus 6, where E equal to number of edges in G, V equal to number of vertices in G. This is number 1. Since the complement of the graph G contains same number of vertices as in G, let E prime be the number of edges in complement of G, G bar. Therefore, E prime less than equal to 3V minus 6. This is number 2. Since G union G bar means complement of G makes the graph complete, therefore total number of edges in G union G bar is V multiplied by V minus 1 by 2. This is number 3. Adding one and 2, we get E plus E prime less than equal to 3V plus 3V, 6V minus 12. Since E plus E prime be the number of edges in G union G bar, that is V multiplied by V minus 1 by 2 less than equal to 6V minus 12, implies that V square minus V less than equal to 12V minus 24, implies that V square minus 13V plus 24 less than equal to 0, implies that V is less than 11. This is number 4. But the given graph has 11 or more than 11 vertices. Therefore, we get a contradiction. Therefore, our assumption that the graph G and its complement both are planar is wrong. Therefore, the graph G and its complement together cannot be planar. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.